So the next topic is called position time graphs. So a position time graph is a graphical way to outline an object's position at every moment in time. The vertical axis is position and the horizontal axis is time. So it looks like this. We'll have two axes here, and position, which is a D with the harpoon, is the vertical axis, and then time is the horizontal axis. Okay, we're going to show you one example first. So referring to the diagram, a gazelle begins at A, trots at a constant pace of 2 meters per second until it reaches B, then runs to C, arriving there 3 seconds after it left B. We're going to draw a position time graph, and then we're going to answer some questions about it as well, such as the distance traveled, displacement, average speed, and average velocity. Okay, so I'm going to give myself some space here to do that. So position time graph, I'm going to have my two axes. Try to make that a bit straighter. Okay, so D for position, I'm going to write the units and direction down as well. So the units are going to be meters, just based on what I see on this diagram here. And the direction, I guess the positive direction would be to the right, and the negative direction is to the left. So I'm going to label the positive axis as right. And then the other axis is T for time. And I believe we'll be using seconds, just when I read the question. They mention seconds and they mention meters per second. Okay, now we're going to have to put an appropriate scale onto the axes. So in terms of position, I can see that the highest position it ever reaches is 20, and the lowest position it ever reaches is -10. So I'll just make sure that I have increments that will cover that range. I think going up by 5s is a good idea here. So 0, 5, 10, 15, 20. And then -5, -10. And that's really all I'll need to do for the position axis. In terms of time, how long is this all taken? So I have to do a little bit of math here. From B to C, it takes 3 seconds, but how long does it take to get from A to B? I have to calculate that actually. So from A to B, based on the diagram, it traveled a displacement of 10 meters to the right. Okay, it started at 10 and it went to 20. So that's a displacement of 10 meters to the right. And it says it did that at an average, constant pace of 2 meters per second. So just doing a basic division here, time will be the displacement divided by the velocity. It's 10 divided by 2, and that's 5 seconds. Okay, so it took 5 seconds to get from A to B, and 3 more seconds to get from B to C. So I'm going to need my scale to go up to 8. So I'll just say 1, 2, 3, 4, 5, 6, 7, 8. Yeah, so sometimes you have to do some pre-work, some pre-calculations, before you can label the scale properly. Okay, so now I'll just draw the position time graph. So I'm going to start, it starts off at A, and A is located at the 10 meter mark. So I'm just going to put a dot at the point 0, 10. And that point is 0, 10. That's a time of 0 and a position of 10. Then at point B occurs at 5 seconds, and it made it to a position of 20. So I'm going to put a point at the point 520. So 5 seconds, it got to a position of 20. And then position C, 3 more seconds later, it ended at a position of -10. So I'm going to add 3 seconds. That'll get it to 8 seconds. And draw my point down at -10. Okay, so at the 8-second mark, it reached a position of -10. So what I'm going to do is join these points up. You should always ask how you should join the points up, whether you should use a straight line or if you should draw a curve. So the words constant pace means it's running at a nice consistent pace. That actually indicates that you should connect the points with a straight line. Okay, so that's a straight line there to get from A to B. From B to C, it doesn't say, if you read the question, it just says it runs from B to C. So it doesn't say if it's at a constant pace or not. So you can actually connect the B to C however you wish. Make sure you do a functions, like don't break the vertical line test. But I'll just decide to keep it simple and just draw a straight line from B to C as well. Okay, so that's A, B, C. And that's an example of a position time graph. It just keeps track of the position of the object as time goes on. Now, part B, we want to know the distance traveled. Okay, so how do we get the distance traveled? The distance traveled, if you remember, it's the total length of the path traveled. Total length of path traveled. I'll just say total length of the path. So I can actually just refer back to my original diagram here. First it traveled 10 meters to get from A to B. And then it went from B to C. Let's make that a bit straighter. From B to C, it went from 20 to -10. So it went 30 more meters. So the distance should actually be 40 meters. And that's no different than how we did it in earlier lessons. But what if you weren't given that number line? What if you were just given this graph? You'd have to actually do the same thing, but look vertically. So from A to B, it actually went up by 10 meters. Okay, you have to look how much it went up by. And then from B down to C, it went down from 20 down to -10. It went down by 30 meters. And then realize that you add those together, 10 plus 30 is 40, and that gives you the total distance that the object traveled. So it's trickier to calculate it just from this graph versus the number line from before. Okay, I'll leave those there. Okay, 2, the displacement. So got to recall what the word displacement means. So displacement is a straight line or a straight arrow from the start to the stop, or to the end. From the start to the end. So I'll change colors here. So using the number line, we've done it with a number line in the past. If we start at A, and we only look at where we ended, which is C, and we draw a straight arrow from where we started to where we ended, we see that the arrow points left, and the length of the arrow is 20, because from 10 to -10, the length is 20. So I would write down 20 meters left as a displacement. So that's how we did it with a number line. We have to be able to do it with a graph now. So similarly, if we start at A, which is at 10, and we look at C, we draw an arrow until we get down to where the ending point is, which is at -10. So we find that this arrow is -20. It's 20 meters and it's pointing downwards, which is a negative direction. So that's how you would find it if it were given from a graph instead of a number line. You have to be able to do both. Now we're going to do some calculations: average speed, average velocity. So 3 is the average speed. So you're going to go with the formula for average speed. which is distance divided by time. And the distance was the answer to part 1, which is 40 meters. And the time is 8 seconds. The whole thing took 8 seconds. So 40 divided by 8 is 5 meters per second. That's the answer to 3. And then 4 is the average velocity, which is the formula displacement divided by time. So this one is 20 meters left divided by 8 seconds. So that would give 2.5 meters per second left. Okay, that would be the average velocity. Okay. So that's one example of a position time graph. This slide is basically some notes on what I was just talking about. Okay, so it's really, really brief. I spoke about it in more detail, so all of that is summarized in as short of sentences as I could. So I'm not going to read these out. You can take the time to see if you can understand what these sentences mean and how it relates to what I said when I was solving the previous question. Okay, so we're going to do it for another example, and so we're going to try to do it without a number line. We'll just have the graph now. Okay, so A. I want the distance traveled from 0 to 5 seconds, the first 5 seconds, and then from 5 to 10 seconds, and then from 0 to 10 seconds, which is the whole thing. Okay, so I'm breaking this down into parts. From 0 to 5 seconds, that's the first chunk of the graph. I see that it started at 15. And it went down to -10. Okay, so from 15 down to -10, that's a distance of 25 meters. And then from 5 to 10 seconds. So at the 5-second mark, it was at -10. And at the 10-second mark, it eventually got back up to 0. So to get from -10 up to 0 meters, that's 10 meters. So then in total, the total distance is when you add the two together. Right? So when you add the two together, that makes a total distance of 35 meters. Okay, now we'll do displacement. So displacement, for number 1 and number 2, it's the same, but we just got to add a direction to it. So from 0 to 5 seconds, it still went 25 meters, but the direction it went is backwards. So looking at how the axis is labeled, it's labeled with an F, which means forwards. So since it went the opposite way from A to B, I'm going to write backwards. And then from 5 to 10 seconds, it went 10 meters, and the direction it went this time is forwards. Okay, if you start at -10 and you go up to 0, you're actually going in the positive direction, so you're going forwards. Now the total, so from 0 to 10 is the total. We're going to add these, but now we have to be careful. It's 25 meters backwards plus 10 meters forwards. Okay, so that's actually, you can think of it as, you can think of 25 meters backwards as -25 meters forwards. So we're actually adding -25 to 10, and that makes -15 meters forward. So I'm just highlighting that there is a big difference between distance and displacement. The distance here, the answer is 35 meters, but the displacement, the answer is -15 meters forwards, or +15 meters backwards. Okay, now we'll calculate average speeds. So average speeds, we would just take all of our answers from A, the distances, and divide them by the times. And what's the time? Well, from 0 to 5 seconds, we divide it by 5 seconds. From 5 to 10 seconds, the time is 5 seconds as well. And from 0 to 10 seconds, it's 10 seconds. So I'll just write that off to the side here. These are the time intervals for the 3 questions. So we're going to take our answers to A and divide them by those time intervals. So the first one will be 25 divided by 5, giving us 5 meters per second. The second one, the distance was 10, and we're dividing it by the time interval of 5. That gives 2 meters per second. And the third one, we had an answer of 35 meters for distance. And we're dividing this one by 10 seconds, because it's from 0 to 10 seconds. And that gives 3.5 meters per second. So those are the average speeds. And for average velocities, we will take our displacement answers from part B and divide them by the same time intervals. So for the first one, the displacement was 25 meters backwards. We're dividing this by 5 seconds. So that'll give 5 meters per second backwards. For the second one, we had 10 meters forwards as our displacement. Now we're dividing it by the time of 5 seconds. 10 divided by 5 is 2 meters per second forward. And then the third one, we had a displacement of negative 15 meters forwards. We're dividing this by a 10-second interval. So that'll end up as negative 1.5 meters per second forward. All right, so that's distance, displacement, speed, and velocity when you're given a position time graph. So far, we've dealt with straight line segments on our graphs, but you're going to be seeing curves in the graph as well, and you need to understand what happens during curves. So there's one very important principle you need to understand about graphs in general, is that the steeper the graph is, the greater the rate of change is. In this case, our rate of change of the graph represents the speed. So the steeper the graph is, the faster the object is going, the higher speed it has. So if I drew a graph, a position time graph, and it was really shallow, I would imagine the object is moving pretty slowly. I mean, it does depend on what the numbers say on the scale. If we have the exact same scale, but a different object makes a graph that's much steeper, then that object is moving at a faster speed. Okay, so the steeper the graph, the faster speed it has. So when you have a curve, for example, something looks like this. What do we say about the steepness of the curve? Well, the steepness, it's not consistent, so it's actually not moving at a constant speed. The steepness, in this case, it's getting steeper as we go. Okay, as time goes on, the curve is getting steeper and steeper. So this would be a graph where I would say the object is speeding up. It's getting faster. It starts off slow and then ends off faster, so it's speeding up. And that's what I want you to be able to recognize based on these slides, or this slide here. Okay, so the graphs down below, the first graph is totally horizontal. It's totally horizontal. So it's actually staying in the same spot. So you would say that this graph is at rest. We're describing the motion of all these objects here. That one's staying at rest. The second graph, I would say that it is, since it's a straight line, it's moving at a constant speed, or a constant velocity even. The next one is also a straight line. So I would also say that this object is moving at a constant velocity. Okay, so it's not slowing down, it's not speeding up, it's going at the same velocity the whole time. What's the difference between the second and the third one? Well, in the second one, the slope is positive. The third one, the slope is negative, if you remember your positive versus negative slopes from math. All that influences is which direction the object is moving. The second one I would say is moving forward, and the third one is moving backwards. Okay, the fourth one, now we have a curve. So this curve, in my mind, it starts off very steep. Okay, the very beginning part of the curve is very steep. And then gradually, it's getting less steep and less steep and less steep and even less steep. So it's getting less and less steep as it goes. So I would say this object is slowing down. The speed is gradually decreasing. It might be a car that it has stepped on the brakes, and so now it's gradually slowing down until eventually it stops. The next graph, it's starting off steep or shallow. Well, that looks pretty steep to me. And then it's leveling off. It's leveling off. It's flattening out. So again, we start off steep and we end off flat. So we're slowing down again. What's the difference between these two? Again, the direction. One of them is moving forward. The other one is moving backward. Okay, now the next graph. It's another curve. We are starting out pretty flat. We're starting out pretty flat. We're getting a little steeper and then a little steeper. And we're ending off actually quite steep. This graph is spiking upwards really quickly. So we started off slow and we ended off fast. So this object is speeding up. And the last one is the same thing, but just going the other way. So we're starting off pretty flat. We're starting off pretty slow, getting steeper, getting steeper. Now we're really steep. So we started off slow and we got really fast. This one is speeding up as well. It's just moving in the backwards direction because the graph is going down. So this is a qualitative description of what the object is doing. We didn't say any numbers. We just described the quality using words like faster, slower, and forwards and backwards, or constant velocity. We'll put specific numbers to it a bit later. Okay, so next, tangent lines and instantaneous velocity. First, the definition of a tangent line. It's a math word. Suppose that point P is a point on a graph. A tangent line at P is a line that touches the point P and has a slope that equals the instantaneous rate of change of the graph at P. So I drew one down below to try to show you what's meant by that. So you pick any point P on a curve, and for that point, you can talk about the tangent line. So I drew a blue line that's supposed to be a tangent line. So the two conditions are it has to touch the point P, which it does. It touches the point P. The second condition is that the slope of my blue line needs to be the same as the instantaneous slope of the curve. The slope of that line has to tell me how steep that curve is at that exact spot. Since it's a curve, the steepness is changing gradually, but the tangent line is supposed to represent how steep it is exactly at one moment. Okay, so those are the two conditions. It's tough to draw tangent lines at this stage. You just kind of have to eyeball it. I like to use a spaceship analogy, so I'll use another color here. So imagine I'm in a green spaceship here, and I'm following this curve. I'm flying through space in my spaceship, and then when I get to the point P, my engines die. I completely lose my ability to maneuver the spaceship. So I'm in outer space. What happens in outer space if you don't have any engines? Well, you end up floating away in a straight line. In whatever direction you left off in, you're going to float away in that straight line. And I can come from the other direction. I'm in a spaceship. My engines are working properly. I'm maneuvering. I'm turning. I'm turning. I'm turning. I get to the point P, and then my engines die. Again, my engines die. So since I'm in outer space, there's no gravity, no nothing. I'm just going to float off in a straight line in whatever direction I was moving at that very instant that my engines died. So that's one way to, I guess, like a metaphor or analogy or something about how to draw a tangent line. But mathematically, it just has to satisfy the two conditions that I wrote at the top. Okay, so why do we care about tangent lines? So when you draw a tangent line, the slope of that line is going to be the instantaneous velocity of the object at that exact moment. Okay, so that's why we draw tangent lines, is to find instantaneous velocity. Now, I'm going to generalize it to just graphs in general. We draw tangent lines on graphs to calculate instantaneous rate of change. Okay. So rate of change is a more generic term. It can apply to anything. It can be a speed. It can be how quickly your portfolio is growing if you're talking about some investments and you draw a graph out of it. It can talk about how quickly the water level is rising if it's raining really hard, if you draw a graph out of it. So it doesn't always have to represent speed, as in distance over time. It works with any graph, really. And we're just generically going to call it the rate of change. Okay, so we'll apply that in this last example here. So there's a graph. So it's actually got some straight sections and it's got some curved sections. And I want to determine the instantaneous velocity at 4 specific moments. Okay, so I guess I'll color code it. I'll start with black. Part A will be done in black. So at the 1 second mark. Okay, at the 1 second mark, what's the instantaneous velocity of this object? So first, I'm going to draw my point at the 1 second mark. And to find the instantaneous whatever, instantaneous anything from a graph, we're going to draw a tangent line. Okay, so I need to draw a line that touches the point, and the slope of the line has to match the instantaneous steepness of the graph. Well, you know what? This part of the graph is already straight. We're lucky. This part of the graph is already straight. So it's not a curve. It's got a constant velocity. So to calculate it, all I really need to do is calculate the slope of this line segment right here. And to calculate slope, if you forgot, we go rise over run. So I'm going to draw myself a little triangle. My rise looks to be from -2 up to +2. So the rise is 4. And my run looks to be 2 seconds. So the instantaneous velocity is simply 4 over 2, which is 2. The units, let's read the axes here. We've got meters forward, and we've got seconds. So the units of this instantaneous velocity will be meters per second, and the direction will be forward. Okay, so that's the process. Draw a tangent line, find the slope, write down the answer, and make sure you're careful about the units. Let's try it again for the 4-second part. I'll use red. And now I'll put a point there, and now we are on a curve. Okay, we're on a curve, so it's trickier to draw a tangent line. The best is to use a ruler, which I can't exactly do on this iPad here, so I'm just gonna have to draw it freehand. But if you have a piece of paper, it should be a ruler. So I'm gonna make some mistakes and erase them. So if I draw a line like this and call that my tangent line, that's not very good. Just eyeballing it, that line is not the same steepness as the curve is. It's a little bit too steep. A general rule of thumb is if you're cutting through the curve, it's not really a good tangent line. There are some special situations where it is, but most of the time, if you're cutting through it, it's not. So I'm going to try to draw a better one. Try to draw a tangent line like this. Here's my point at 4. I would say that's still not very good. Okay, look on the left side how much the gap is away from the curve. It grows really quickly. And on the right side, it's really tight to the curve. It's not really symmetrical. So another rule of thumb is should be sort of symmetrical on both sides in terms of how close it is to the curve. So, okay, let me try again. That is better. Okay, that is a bit better. It's not great still. It's not perfect, but it's hard to be perfect. When you get to grade 12, calculus and vectors, they'll teach you a way to perfectly determine the line, but for now we're just going to eyeball it. So that's the best I'm going to do. I'm going to use that. I'm going to try to find the rise and the run of this. So draw myself a little triangle, maybe here. Okay, rise and run. So the rise, we're at about 5. We're at about 5, and we get up to about 6 point. Right here is about 6.75. So the rise from 5 to 6.75, I'd say the rise is 1.75. And the run is simply from 4 to 6. That one's simple enough. So that's a 2-second run. Okay, so the slope of that, 1.75 over 2. That would be, that's 7/8. So that would be 0.875 meters per second. And the direction is forward. If the slope is positive, the direction is forward. When we get to 10 seconds, the last question, the slope is actually negative, and that's when I'm going to say backwards. Okay, so the answer there is lower than my answer to A, which makes sense because the graph is getting less steep. Okay, next one is at 7 seconds. I'll use blue for it. So at the 7-second mark, there's 7. It's right here. Okay, so this one is simple. If I draw a tangent line, well, the graph is already pretty straight at that section. It's straight and it's horizontal. It's totally flat. So that's got a slope of 0. So the speed is actually just 0 meters per second there. So if you got a horizontal line, the slope is 0. Okay, the last one, the 10-second mark. Okay, I'll locate the 10-second mark. So it looks like I'm on a curved section. To try to draw a tangent line again, may take a few tries before I'm satisfied with it. So that's not so good. I missed the point completely. Let me try again. Okay, so I think that's the best I'm going to do without a ruler. It's not too bad. So we try to get the rise and the run here. I'm going to draw a triangle like this. to try to get the rise and the run. Okay, so the rise looks like I'm at 4. Like this is at 4. I'm gonna get down to about here, which is about 2.25, 2.25. Okay, so my rise, it dropped. It went negative 1.75. And my run just went from 10 to 11 seconds. So the run is just 1 second. Okay, so the slope is negative 1.75 over 1. So that just makes negative 1.75 meters per second forward. So my answer is negative in this case. The slope is negative. That means the object is actually moving backwards. So I'm just going to say or 1.75 meters per second backwards. All right, and that is it. So tangents are used to get instantaneous rates of change.